Kenny G non-stop.
Ah yeah, check this
Some
out.
Kenny G stop.
Check this out.
Kenny G.
Check this out.
Kenny G.
Ah yeah, check this out.
Kenny G non-stop.
Shake your body, shake your body, rock your body like you never will. Lose to the pound. Skålsiktig energi, appelle-moi ça. Synchronie stabile, je vais prendre des non-stop. Tu verrais ça sur le bas, laisse-moi cramer sur le pop. Tu peux vite, tu peux easy, tu peux cheat, tu peux groove. J'ai un poste de Kennedy dans le salon chez nous. J'ai des couches de suede, des miroirs partout. Des disco balls, puis des potes de loup. Laissez pas me dire que Kennedy est trump, comme des girls de contact. Tu veux son numéro? Sax dans le backdrop, smooth comme un lollipop. Tu sais, tu veux du Kennedy non-stop. Tu sais que tu veux du Kennedy non-stop. Tu sais que tu veux du Kennedy non-stop. Tu sais que tu veux du Kennedy non-stop. Kennedy non-stop. Kennedy non-stop.
Some Kenny G non-stop.
Tu sais que tu veux du Kennedy non-stop.
Kenny G.
Oh yeah, Kennedy non-stop. C'est feedback, c'est tout ce qui sort. Comme ça que ça smooth, comme ça que ça pop. Pas trop compliqué, je suis sharp pour la rap. C'est comme des guilty pleasures, comme toute la journée en vrai. La seule fille qui reste, c'est plus ton bec. Comme ça que c'est smooth, comme ça que ça pop. Et tu n'en veux pas, bah t'en veux non-stop. C'est que tu veux du Kennedy non-stop. Up top, les séminaires, pas sur les séminaires. Les Kennedy, des GoPro, Starbucks on show. Le Kennedy, mais laisse-moi faire mon best. Laisse-moi piloter ta peine avant que je dise des tests. Les Kennedy non-stop. Tu sais que tu veux du Kennedy non-stop. Tu sais que tu veux du Kennedy non-stop.
I want some Kenny G non-stop.
Tu sais que tu veux du Kennedy non-stop.
Kenny G.
Oh yeah, c'est que tu veux du Kennedy non-stop. C'était bienvenue dans mon chanel tour. On écoute du Kennedy jusqu'à la fin de nos jours. Dans mon testament, j'ai qu'une section. D'amener Kennedy à mon entendement. C'était bienvenue dans mon chanel tour. Chanel tour. Tu sais que tu veux du Kennedy non-stop. C'était bienvenue dans mon chanel tour. On écoute du Kennedy jusqu'à la fin de nos jours. Tu sais que tu veux du Kennedy non-stop.
Some Kenny G now, Kenny G, Kenny G non-stop. I want some Kenny G non-stop.
Si tu veux du Kennedy, mon nom c'est Kennedy. Si tu veux du Kennedy, mon nom c'est Kennedy. Si tu veux du Kennedy, mon nom c'est Kennedy. Si tu veux du Kennedy, mon nom c'est Kennedy.
Morning, everyone. Still very early.
Yo, cliche hot, cliche hot, 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 cliche hot, 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 cliche hot, cliche hot, 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 cliche hot. Cliché hot, je réveille, cliché hot d'amoli, prends marche promenade, cliché vite compris, cliché hot la nouvelle mode qui rend ta vie, tes culottes, hop, j'entends aussi, cliché hot, personnage qui vit au ciel compris, cliché hot, la mode à elle ou la mode à lui, c'est cliché hot, t'es compliqué, des clichés hot, t'es conflit, cliché hot, la mode à l'homme qui est pas ton senti, belle fille qui rentre dans la place, c'est si jolie, avec ses orteils, belle remplie sa face aussi, cliché hot, c'est l'idiot, tu la vois dans ton lit, cliché hot, la folie, et elle te dit, moi aussi, pas capable de voir un cliché, mon corps t'écoute. Tu sais qu'est-ce qui est cliché? Mon pop bébé free, j'ai dit une vraie, troisième préposé, t'as pas besoin de prescription, ta première bébé free, yo, cliché hot, cliché hot, cliché hot, yo, cliché hot. Cliché hot, cliché hot, cliché hot, c'était cliché hot. C'est qui fait des dodgy coco dans notre, c'était hot, c'était cliché hot. C'est qui fait des dodgy coco dans notre. Je vais pas te mettre sur le spot, mais t'es cliché hot. Porte une skirt dans les verres, comme une forme de pomme de terre, look at there. Le check le Gino pour la lèche, mise ouvert. Le tiers d'un pièce, va t'acheter du nerf. Une douce moustache comme un jeu de billard, c'est le stéréotype, oui, c'est cliché hot. Le gangster, oui, t'es gangster. Big chain, illégal dans les vidéos. Cadillac avec un corps dans le coffre. Qui c'est la main du flic, c'est chic. Original, celle qui pense de faire ça. Regarde ça, des troupes sortent, petite culotte avec un nom whisky. Dans l'élastique, des rimes faites en plastique. C'est fantastique. Déjà vous, comment allez-vous? What you get the review? La cliché hot, madame avec le tout top. Parfait combinaison, faite pour la saison. Mettez ça en raison. Cliché hot. Cliché hot, c'est tout c'est cliché, ouais c'est cliché hot. Cliché hot, cliché hot, cliché. Arrache ta chemise, bitch, c'est cliché hot. Cliché hot, cliché hot, c'est cliché hot, c'est cliché hot, cliché hot, cliché hot, c'est cliché hot, c'est cliché hot, cliché hot, cliché hot, cliché hot. Je veux point mettre sur la spot, mais t'es cliché hot, urban style, turn fit. Y'a des femmes qui t'écrasent à la gueule de vieille femme comme un changement de nom. 3 jours à la mode, 4 jours d'excellence. So, écoute le sound qui dit que t'es belle, je te dis que t'es belle, c'est ça qui veut. Positive reinforcement pour les enfants. On jet never mind, le boss il never monte. Refuseront, le rejecteront, le traduiront, puis il finiront. Alors t'en ce qu'il acclameront. Ils l'écouteront et diront que parce qu'il aime. Oh ouais, y'a ta grace, c'est à mon favorite. Révolutionnaire, il faisait vraiment de la suite. Avec une fois que t'es gone, veux-tu souvenir ton image à la mode, mais t'es personne t'a vu. Un risson, tout le monde le veut. Un risson, tout le monde est né. Un risson, tout le monde le voit. Un risson, tout le monde est là. Un risson, tout le monde le veut. Un risson, tout le monde est né. Un risson, tout le monde le voit. Un risson, tout le monde est là.
Morning, everyone.
C'est basically la même affaire que les lessons.
Mountain Time, parce qu'on a quand même mis des diffusions. Exact, bare feet in the heartbeat. Bare feet in the heartbeat. C'est ce qui est nice. Yeah, c'est ce qui est nice. Comme tes hanches sont nice.
Ouais.
J'aime ta danse, c'est nice.
Mes souliers.
Les cheveux sont nice.
Right.
Mais c'est les autres.
Non, je peux bien faire comme ben avant que tous deux gars, puis on est fait faire une compétition entre les Penelope et le deck show.
Avant que je gagne d'avance.
Ben, how about qu'on fasse du tails?
Let's go. Alright. Leave it to be.
So, heads, the Penelope for tails selection.
Straight to the point, je gagne. Ben avant que laisse pas
Macarena superstar, marcher sur la main, marcher sur la auto. Any, many, money, c'est qu'est-ce qui fait du jello? Si Cosmo, c'est du vélo. Come on, baby, hello. So, dans tout la sans marcher sur la hay. Ok, j'explique, c'est dans ma minivan, no they got you. My case in the case, my case was wrong. My case in the case, my still was wrong. Pick it over, you got that soul, got that shit, my. Now I'm wish work my time, shopping, channel, all that scam. Copy, call this shit, go bang. Basically, so basic, so I make it back in low phone, I make it shoot. Don't show my shit, so loud. Don't show my shit, so loud. I make it back in low phone, I make it back shoot. Don't show my shit, so loud. Don't show my shit, so loud. So please, go, n'ayez payé ma shit, so loud. Hey, j'ai dit plus, go, n'ayez payé ma shit, so loud. Pour un sense à mon nom, cause de Louis Vuitton. And down the deck, shoes, pas de bateau, un peu métal. C'est vrai que ça se passe. jacuzzi. Je suis pauvre, je dirais plutôt je suis broke. Quand ça ne compte rien, abonné sur la côte. Non, j'aime les couchers de soleil, puis watcher les bateaux avec de lazy listening jazz qui joue sur mon radio. Avec des paniers locaux, avec des belles choux, je vais marcher cela, je vais marcher cela. Avec des paniers locaux, avec des belles choux, je vais marcher cela, je vais marcher cela. C'est my life aquatic, and I'm not avec mes belles choux. Je marche sur la haie, je marche sur la roue, je marche sur la baie, le jour où je fais sans rien de bleu. Je marche en peu des causes, je croyais en rien du tout. C'est la new edition, television, match que je fais, no. Tout ça de monde qui sait, tout le monde croit qu'il faut. Tout ça de monde qui croit, les histoires des matelots, moi je les ai trouvées sur la boutique chaque en marchant sur la wall. So please, bro, yeah, marcher sur la haie, j'ai dit please, bro, yeah, marcher sur la haie. Please, bro, yeah, marcher sur la haie, j'ai dit please, bro, yeah, marcher sur la haie. Avec les paniers locaux, avec les bacs choux, je vais marcher sur la haie, je vais marcher sur la haie. Avec les paniers locaux, avec les bacs choux, je vais marcher sur la haie, je vais marcher sur la haie.
How we doing, folks? I think we have time for one more.
Ha! You see it? Yo! J'ai de la place en masse dans mon jacuzzi. Voulez-vous venir dans mon jacuzzi? Y'a de la place en masse dans mon jacuzzi. Voulez-vous venir dans mon jacuzzi? Le jacuzzi plein de clowns, c'est le festival. Un jacuzzi extra large, on fait des fêtes de cheval. Ma jacuzzi, baby, toi, submarine, watch-toi. GPS sous l'eau, nouveau jacuzzi. On boit du homemade wine et 12 bouquets. Dans jacuzzi, believe you me. Oh, voilà, j'ai changé moi de cruise. D'abord, toute ma jacuzzi. Je sais qu'il veut venir parce que je vois de jalousie. Pop that, j'fais une boule dans ma jacuzzi. Pas de bedding sous le sunroof, ma jacuzzi. Jacuzzi, comme dans les movies. Les chauffeurs, je suis cool, puis les femmes de mon sang. Avec l'eau, je suis pleinement comme les femmes que j'aime. Ma jacuzzi est trop belle pour lui, je scratch. Y'a de la place en masse dans mon jacuzzi. Voulez-vous aller dans mon jacuzzi? J'ai de la place en masse dans mon jacuzzi. Voulez-vous venir dans mon jacuzzi? Dis-moi là ce que j'ai vu dans mon jacuzzi. J'aimerais mes vidéos à faire dans mon jacuzzi. Y'a des contestes pour des fuck dans mon jacuzzi. Y'a des lobbies des sages qui se battent dans mon jacuzzi. Je porte une douche dans ma jacuzzi. Ma vie a changé depuis que j'ai une jacuzzi. Je mange des onion rings dans ma jacuzzi. Chaque jour c'est Noël, puis je break one. J'ai une douche jacuzzi, juste comme dans les movies. Les chauffeurs, je suis cool, puis les femmes de mon à l'église, puis pleinement comme les femmes que j'aime. Ma jacuzzi est trop belle pour plus je scratch. Y'a de la place en masse dans mon jacuzzi. Voulez-vous aller dans mon jacuzzi? Écoute la musique qui joue sur mon proximité. Et c'est tout 17, là ça s'appelle jacuzzi. Sur une gueule, mon jacuzzi, le monde surf, envoyé de notre tête, donc il fait des steps. Moi je te dis dans mon jacuzzi, la vie est simple. Je dans les condos, ils veulent tout ma jacuzzi. Porte tous les secrets, j'ai fait pour ma jacuzzi. 2 millions de tous les semaines pour ma jacuzzi. Private jet landing strip pour ma jacuzzi. Ça prend une autre planète pour ma jacuzzi. Tout le monde se peut mettre dans ma jacuzzi. Ça prend une autre planète pour ma jacuzzi. J'ai une douce jacuzzi, juste comme dans les movies. Les chauffeurs, je suis cool, puis les femmes de mon sang. À l'église, puis pleinement comme les femmes que j'aime. Ma jacuzzi est trop belle pour lui, je scratch. Y'a de la place en masse dans mon jacuzzi. Voulez-vous aller dans mon jacuzzi? J'ai de la place en masse dans mon jacuzzi. Voulez-vous venir dans mon jacuzzi? Tu peux voir ma jacuzzi de la deep space. Dans l'église, gas power, puis le moteur float. Assis sur mon tour avec mes chaises cell phone. J'ai des calls qui me réveillent à cause de cette time zone. Easy breezy, beautiful jacuzzi, beautiful jacuzzi, beautiful jacuzzi. J'ai de la place en masse dans mon jacuzzi. Voulez-vous venir dans mon jacuzzi? Y'a de la place en masse dans mon jacuzzi. Voulez-vous venir dans mon jacuzzi?
questions before we begin? No, we're good. Back to related rates then. Consider the following scenario. I don't know anything about Discord and the WhatsApp business. I'm not running those. Number 18, a spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of the shadow on the building decreasing when he is 4 meters from the building? All right, so let me write that down. Spotlight on the ground. Shines on a wall 12 meters away. A man 2 meters tall walks from the spotlight towards the building. At a speed of 1.6 meters per second. How fast is the length of the shadow? On the building, decreasing when he is 4 meters from the building. That's the question. So first I suggest, what's the difference between the length of the shadow and how far the man is from the wall? Why does the question have to incorporate this? Well, let's draw a picture, right? As Hamza suggests, why don't we draw a picture? Seriously. Why don't we draw a picture of what's happening to understand the question better? So we have a spotlight on the ground. And this is shining on a wall 12 meters away. And then you have this man walking towards the building. So you see what happens, right? I mean, here, you're going to have this big shadow if he's very close to the spotlight. And if he's closer to the wall, the shadow is smaller until he's right at the wall where the shadow is just going to be the height of the guy. So you see that the length of the shadow is getting smaller as suggested by the question. And as Kripa suggests, we're going to have some triangles happening here. Absolutely. Let's start by introducing, well, right, I mean, Paul is asking the good question. What is the question asking? So if we let L be the length of the shadow, so let's introduce some variables. Let L be the length of the shadow. We want dl dt. That's what we want. Absolutely. Now what's given? What's given is that the guy is 2 meters tall. And also that the guy is walking towards the building at a rate of 1.6 meters per second. So how are we going to incorporate that? Well, if we let x be the distance away from the spotlight, or be the, well, distance or if you view this as the x-axis, x of t is going to be the position of the man at any time t, right? If the spotlight is positioned at the origin. So dx dt, the rate of change of the position, is the velocity, which is 1.6. Pamela is asking if all these questions are in terms of time. Well, you know, you have to adapt. You have to adapt. Quite often that's the case, but it might not necessarily be. So there it is. We have this business. This is what's given. This is what we want. So my question to you is there a relationship between L and X? Can we find a relationship between L and X? Right, this is going to be your L here. L of t, because as the man moves forward, the length is getting smaller. So is there a relationship between L and X? That's the question, right? And let's look at this big triangle right here that I think will give it to us, right? Right angle triangle. But you also have another right angle triangle right here, where this, the position of the guy, x of t, so this is x of t, this is of course going to be 12 minus x of t, if we need it. I'm not familiar with Thales' theorem. We haven't seen it in class, so no need. Similar triangles does the trick here. I believe. Right? I mean, you have this small triangle right here. So tangent, right? Let's call that angle theta here. Tangent to theta is going to be opposite over adjacent. So it's 2 over x. But it's also the big triangle. So opposite over adjacent. So this is also L over 12. Thank you, Leela. Could be Lila. It's not clear at this point. Red suggests that the height of the guide does not change, and that's correct. But we always have this, right? I mean, L is changing to compensate. So there you have it. In other words, L is 24 over x. We don't need to work with our 10, right? Tangent of this angle is that over that, or that over this. And that's sufficient. So you have this nice relationship between L and x. And that's really all we needed. Right, so L is 24 over x. And if you differentiate the whole equation with respect to t, you get dl dt. Derivative of this is negative 24 over x squared dx dt. Dx dt is given as 1.6. We want dl dt when the guy is 4 meters away from the building. So if the guy is 4 meters away, x is going to be 8. Right? To be 4 meters away from the building, it means that x is 8. And so this is minus 24 over 8 times 8 times 1.6 or 16 over 10. This is 3. This is 2. So that's 1 over 5, negative 3 over 5. Is that right? Negative 3 over 5. Jack is asking about quotient rule. Fine, if you want to use the quotient rule. I was treating this as 24x to the negative 1. So easier than, faster than using the quotient rule. So negative 3 over 5. Negative, right? We were expecting that the negative corresponds to the decreasing business. Right? The rate of change. The shadow is getting smaller. So that's why we have a negative as expected. And there it is. Why did we multiply by dx dt? Well, we were differentiating with respect to t. So dl dt is dl dx, dx dt, chain rule. Do we need conclusion statements in this class? You should probably make sure that you answer the question. Let's say this. Make sure you answer the question. So you should write a sentence saying, consequently, the shadow is decreasing at a rate of 3.5. meters per second. Why is theta the same for both ratios? Well, I mean, when you fix a theta, you essentially have two triangles, the small one and this big one. Connor is suggesting that these questions are kind of confusing, and again, they are tricky. Right? I mean, the first thing to do is translate the question into mathematics. You can leave it as 1.6. I mean, the final answer is what's important here. Andrew is still unsure about this dx dt. We had convinced ourselves originally that we wanted dl dt. But L was given in terms of x. So when you differentiate with respect to t, x was understood to be a function of t. So dl dt is dl dx, dx dt by the chain rule. Right, let me write that down. dl dt is dl dx, dx dt. This is the chain rule. dl dx is this business, and dx dt is that. So minus 3/5 is the final answer. The final answer should be the shadow is decreasing at a rate of 3.5 meters per second. 3/5 meters per second. Right, so Connor was saying that these are tricky, and they are. You're absolutely right. But the more you do, the easier everything becomes. And the idea is this. First, you have to translate the problem into mathematics. Perhaps a diagram of what's happening may be helpful. 16/10 is 1.6. That's the x dt that was given. So translate the question into mathematics, introduce some variables, maybe draw a picture of what's happening, and then ask yourself, what is the question asking for? And what is given? Write all of these things down. And then, as the question suggests, these are related rates. You're looking for a relationship between what you want and what is given. Yeah, exactly. Right? Translating is a bit tricky because if you make a mistake in the beginning, everything is wrong afterwards. Yeah. Yep. You're right. All right, let's move on. Move on to the idea of linear approximation. Bree wants to do the following question. Let's do it. Is this a question on my courses? I haven't released my courses yet, right? The web work, I mean. Right. All right. So water is leaking out of an inverted conical tank. So you've got a cone with some water. Water is leaking out at a rate of 10,000 cubic centimeters per second, per minute. At the same time that water is being pumped into the tank at a constant rate. So water is being pumped into the tank at some rate R that we don't know. So R cubic centimeters per second. If the water level, the tank has height 6 meters. And diameter at the top is 4 meters. If the water level is rising at a rate of 20, what is that seconds? Everything is in minutes. We're going to stick with minutes. If the water level is rising at a rate of 20 centimeters per minute, so this water level is rising at a rate of 20 centimeters per minute, when the height of, so I guess it's not right back, but let's write it out. The water level is rising. (20 centimeters per minute) when the height of the water is 2 meters. Find the rate at which the water is being pumped into the tank. Is that right? Sorry, thank you for pointing that out. The diameter at the top is 4 meters, so the radius is actually 2 meters. That would have been disastrous. Thank you. Right, so what do we want? We want the rate at which the water is coming in, which we've denoted by R. We don't know what the rate is. Perhaps that was a bad choice, given that we're dealing with a cone and maybe some radius. Let me call it R in, meaning the rate of the water coming in. Pratika's given us the volume of a cone. Is that r squared or should it be r cubed? No formulas will be given on the final exam. Right. Very well. So volume of a, so volume of the cone is given as 1/3 pi r squared h. And let's figure out well, the centimeters cubed is only because we're dealing with volume. Right? Are we expected to know all the formulas for the final? All volume formulas for the final? I expect you to know volume of a box, volume of a sphere. That's it. Area of a rectangle, area of the circle, area of a triangle. I think that's enough. So I don't expect you to know the volume of a cone by heart. And if you needed it for a particular question, I would have given it to you. All right, so we want the rate at which the water is being pumped into the tank. Now, I mean, you understand the idea, right? Apparently, according to the question, the water level is rising. So let's introduce some variables here. Let's introduce some variables. Let h be the height of the water. In the tank at any time h, at any time t. Circumference, yes. So you should know circumference of a circle, perimeter of a rectangle, perimeter of a triangle. Yeah. Or at least know how to figure them out. So let h of t be the height of the water in the tank at any time t. What do we want? We want the rate of the water coming in. Now let's think about this for a moment. We have some water coming in and some water going out. So the volume is changing. Should we know how high the water is when the question starts? Like, is it full? Well, it better not be full, right? Because the question is telling us that the water level is rising. So we expect more water coming in than going out. So if you started out with a full cone, then it would be overflowing immediately. So not what's happening. Maybe the cone was empty to begin with, but apparently it doesn't matter. It doesn't matter because we want at some point in between. So we don't need to know how much water you started out with in the beginning. What's important, right? So I mean, what's going on? Some water's coming in and some water's going out. So the volume of the water is changing. That's the important observation to make. What is the rate of change? What is the rate of change of the volume? The rate of change of the volume is how much water is coming in minus how much water is going out, as Yash suggests. Thank you. Right? That's the rate of change of the volume. So how much water is going in? We don't know. It's the rate going in. That's what we're looking for. So as Gabrielle suggests, we see the water as a cone in itself. Absolutely. Right, so the rate of change, the rate going in minus the rate going out, and it's going out at 10,000 cubic centimeters per minute. There it is. But, right, so this is what we want. If we knew what this was, we'd be in business. And what is that? dV/dt, well, here's your V. So dV/dt, differentiate this. This is d by dt of 1/3 pi r squared h. So the derivative of this, what is that? The pi over 3 is a constant. Let's leave it outside. And then you differentiate this, which is a product. Derivative of the first one, r squared, that's 2r dr dt. Leaving h fixed, and then we'll leave r squared fixed and differentiate h. There you go. Thank you. So, question is, do we have all of these things? What do we want? Find the rate at which the water is being pumped into the tank. We are given that the water level is rising at 20 centimeters per minute. So we're given that the water level is rising. In other words, dH/dt, when the height is 2, this is given to be 20. So now my question to you is, Evan is a bit confused with the logic, finding the derivative of the volume. And so really wait, are you referring to this, or are you referring to the actual first step? If you're referring to the actual first step, why are we bothering with this? Well, that's where the rate going in appears. If you're referring to this, this is just the product rule and the chain rule combined. We have dH/dt, and as per suggests, we don't have the radius. So can we find a relationship between R and H? Right? right? And again, I think the idea of similar triangles appears. Right? If this is the angle theta, you have this big triangle, 6 meters and 2 meters, versus when the height is 2 meters. So versus the smaller one, a height of 2 meters. And well, that's not what. Sorry. If you have a height of h, the question is, what is the radius? Let's call it little r. And what do I want to do? Maybe again tangent of theta. Tangent is opposite over adjacent, so r over h. And it's also opposite over adjacent, 2 over 6. So you see that h, if you solve for h is 3r. Right? Or r is 1/3 h. Probably a better reformulation. R is 1/3 h. So dr dt is 1/3 dh dt. And now we're good to go. Absolutely right. We're dealing with meters everywhere. Everywhere meters except for this 20 centimeters per minute. So we should change this to meters as well, or convert all the meters to centimeters. Either way, whatever you want to do. So convert this to 0.2. 0.02 100 centimeters, so 0.2 meters per minute. And what was the rate? The rate was it. Okay, so maybe change everything to centimeters then. Centimeters. Very well. So let's leave everything in terms of centimeters. Are we actually using meters anywhere else? We might not be. We'll see. We'll see. So 2 meters or 200 centimeters. Yeah, I think it's better to change everything to centimeters, because there's only one thing to change. All right, so let's finish that up. This is what we have here. So pi over 3. The radius, when the height, so fine is being pumped into the tank. So in particular, right, you can plug in that this has to be true for any time t. So in particular, plug in the time when the height is 200 centimeters. And when the height is 200 centimeters, the radius is going to be 200 over 3. dr dt is 1/3 dh dt. And dh dt was given as 20. the H, which is 200 centimeters, plus R, which was 200 over 3, squared, times dH dt, which was given as 20 again. And that whole thing is the rate going in minus 10,000. What is the... Oh, that was 20. Wait. Sorry. dH dt was 20. Thank you. dH dt is 20, and the height is 2 meters or 200 centimeters. This is all in centimeters. Thank you, thank you. But this is still 200, right? Because that's the height, 2 meters or 200 centimeters. The radius of the cone is given as 2 meters. We incorporated that to find a relationship between the radius and the height at any given time using similar triangles, absolutely. It should be 200 in the second term. Thank you. Because it's the height. It's the height divided by 3. Height divided by 3. So 200 was correct here. It was just here. Wait. Shouldn't it not be 200 there again? What am I doing? This is the radius. Yeah, 200 over 3, right? Absolutely, absolutely. So I was right the first time there. It's dH dt, which is 20, right? So dr dt is going to be 1/3 of 20, and dH dt is 20 again, but the rest is 200. All right, we were good. We were good. Yeah, we probably should have written everything down in centimeters beforehand, but there it is. Thank you, Con, for noticing that. There it is. All right. A lot of stuff going on there. Not the least of which is the fact that we're working in 2 different measurements. So don't make the same mistake we did. Convert everything to centimeters from the start. All right, let's take a few minutes to discuss linear approximation. Absolutely, right? I mean, you could have plugged in 1/3 h for the radius, and then you would have just been working with one variable h. It seems complicated. I probably made it out to be too messy. I made it too messy. Redo it. Redo it by changing everything to centimeters to begin with. And really the idea is to find a relationship between the radius and the height. And again, it's just similar triangles. But let's say this. A question on the final is not, this is as complicated as it gets. So you'll be happy to note that you won't get anything harder than this. Linear approximation, recall. What do we want to recall? Recall the alternate definition of the derivative. Limit as x goes to a of f of x minus f of a over x minus a consequently, for values of x very close to a, right? Because you know the limit is the behavior of this for values of x very close to a. Thus, for x close to a, assuming this limit exists, of course, so if your function is differentiable for x close to a, for x close to a, this business is going to be close to the derivative. Well, Jack, you can certainly expect a related rates problem on the final. I know they're difficult, but you can expect one on the final. Bring this over. And bring that over. And there it is. Bree has confirmed that it has worked. Thank you very much. Thank you. Thank you for that. You will get partial credit, right? I mean, hopefully you will faint after having done most of the work. And if that's the case, then you can expect partial marks. So here's the idea of linear approximation. For x close to a, f of x is or can be approximated by this right-hand side. This is linear approximation, sometimes referred to as tangent line approximation, because if you have y equals this, that's really the equation of the tangent line. Exactly. So as Pratik has mentioned, it looks a lot like the tangent line, and that's why it's oftentimes referred to as tangent line approximation. On a graph, what's going on? You have your function, and at some point A, you have the tangent line. What we're saying is that for values of x very close to A, your function can be approximated by the tangent line. So if you take the values on the tangent line instead of taking them on the function, they're more or less the same. That's it. Let's take a few examples. Eddie is asking an excellent question. How accurate of an approximation would this be? It's a valid question. One that we are not able to answer immediately, but one that you will be able to answer in Cal 2, the following course, right at the end. Right at the end of the course, you'll see how to approximate the error. It's probably optimistic. It's 100.5, correct. So it's probably optimistic that you're going to get to there by the end of next semester, but certainly in Cal 3. So when you do Cal 3, for sure, you'll be able to work out how good of an approximation this is. So as Sophia suggests, very nice idea, right? In order to use linear approximation, you need a function. And Sophia suggested the square root of x. And we want to approximate f of x when x is 100.5. And lucky for you, you know a perfect square that is very close to 100.5. Are we going to get our midterm back on Monday? That's the hope. Let's keep our fingers crossed. And you know a perfect square very close to 100.5, namely 100. Thank you. So by tangent line approximation, by linear approximation, f of x is approximately f of a plus f prime of a times x minus a. So what's the derivative? If f of x is this, the derivative is 1 over 2 root x, and the derivative at 100 is 1 over 20. So here, what we're saying is f of 100.5 is more or less f of 100 plus f prime of 100 times 100.5 minus 100. F of 100, or square root of 100, is 10. Derivative of 100 is 1 over 20. And 100.5 minus 100 is 0.5. So that's 10 plus 1 over 40, or 401 over 40. A nice number that you can calculate without a calculator. Whereas to get anything good, you need a calculator to figure out what that is approximately. Close to 10 for sure, right? Because this is very close to 100. But there it is. Linear approximation. But if the perfect square is not immediately obvious or very far away, right? Because this is valid for values of x close to a, then you're in a bit of trouble. Do we want to do one more? Or are we good to go? Let's do one more. How close do you have to be for this theory to be valid? Again, a valid question. A question that we don't have the tools to answer right away, but again, Cal 3 is where you'll be able to answer this. I mean, I would have accepted either answer here. Would have been. Cosine of 29 degrees, you know that nobody works in degrees. Let's change this to radian measure. Cosine of, well, 29 pi over 180. And the value close to 29 pi over 180 that we're going to take. Well, so first of all, we need a function. Function is obviously going to be cosine x. And you're going to take a, as Pratik suggests, and a few others, pi over 6, namely 30 pi over 180. Which is pi over 6. You know cosine of pi over 6 and sine of pi over 6. Right, so for values of x close to a, f of x is approximately f of a plus f prime of a times x minus a. So let's figure out the derivative. Derivative of cos is negative sine. And the derivative at pi over 6, sine of pi over 6 is? You know what sine of pi over 6 is? Sine of pi over 6 is 1/2, thank you. So negative 1/2 for that. So here, f of 29 pi over 180 is approximately f of pi over 6 plus f prime of pi over 6 times 29 pi over 180 minus pi over 6. or minus 30 pi over 180. So what is this? This cosine of pi over 6, people have suggested already that this was root 3 over 2. The derivative at pi over 6 is negative 1/2. And this 29 minus 30 is negative pi over 180. And there we have it. Root 3 over 2 plus pi over 360. Well, I mean, you have a negative out front here, right? So you have no choice but to use what's happening, right? I mean, we cannot make anything up there. So the derivative is negative sine. So the derivative at pi over 6 is negative 1/2. Is sine of pi over 6 not 1 over root 3? No, I think it's 1/2. Sine of pi over 6, right? I mean, you know those triangles, those important triangles. All right. How are we doing? Questions? All right, well, thank you. Thank you all for coming. So practice this. I don't think there's much going on here, right? I mean, you're always using this idea, this tangent line approximation. So when the question is asking you to approximate something, you got to come up with your own function. You got to come up with a value of a that is relatively close. I think I'll post a new web workout there. There's probably one on related rates that I can give you access to. So I'm going to do that right now. Have we done everything from 3.5 to 3.10? I think we skipped, well, first of all, in this section, there's something called differentials. We're not going to do it. We also skipped exponential growth and decay. I mean, there are very nice examples, in particular, Newton's law of cooling, which is, they discuss that in that section. It's very nice, but, you know, I mean, since the audience is very diverse and not everybody's done physics and chemistry and all that, plus, I mean, we are running out of time. I mean, we're not in a rush or anything, but yeah, so we're not going to spend any time on that. All right. Right, as Connor suggests, linear approximation should work for differentiable functions. Right, that's really the only thing you need here. As long as the function is differentiable and x is close enough to a, you're good. Well, I mean, physics is very nice. So, plus, you know, I mean, we're doing a bit of physics anyways, right? In the sense of position versus velocity and acceleration. So that'll be enough for us. All right. Well, thank you all for coming, folks. You guys have a good weekend, and I will see you on Monday. Hopefully the midterm will have been completely marked by then. You guys have a good one.